Okay, so before we do the example, I wanted to just emphasize something that I didn't mention in the first video. And so I did say that the definite integral gives you the area of a curve over some interval, the area under a curve, that is. So if we think about what that means that this thing right here, which is our definite integral, and it's defined via this limit, it should be a number, right? So what comes out of this computation is going to be a number. So just keep that in mind when we are going through these calculations. Okay, so here we are going to first write this integral right here. So this is the function part, and then we have our dx. And then we are going to first write this as the limit of a Riemann sum. So we'll figure out what it is we need to take the limit of, and then we will evaluate it. Okay, so first let's figure out what delta x is going to be. So notice our interval is 0 to 3. And I get this from the bounds on the function. So the bottom bound is 0, the top one is 3. So 0 to 3 is the interval that is. Okay, and then knowing the endpoints of the interval, we can compute delta x. So remember, delta x is b over a minus n. Since we're writing this as the limit of a Riemann sum and we want to take the limit as n goes to infinity, we leave n as just a variable, right? Because we're going to use that and take that to infinity. So this is going to be just b minus a, which is 3 minus 0. So delta x is 3 over n, right? And then what we're going to do is oh, I forgot to include that. Sorry. So we need to actually specify which endpoints we're going to use, or what sample points we're going to use. So maybe I'll write this in a different color because it should be part of the problem. So we'll say using right endpoints. And a lot of the time we use right endpoints because they are the most convenient ones to use, and you will see why. So notice that if we start off with just figuring out what our endpoints of our intervals should look like, what we will have is x0 starts with 0 because that's the first point, or the left endpoint of our interval. And then x1 is going to be 0 plus 1 jump, so 1 copy of delta x, right? So that's 3 over n. And then we'll do like this. x2, you are going to be taking x1 and adding another copy of delta x, so 3 over n, so you get 2 times 3 over n. And x3 is the same. You add 1 more copy of 3 over n, so you get 3 times 3 over n. And you can continue this. So for each I in the interval, what xi is going to be equal to is I times 3 over n, right? So we're just following the pattern. Okay, so we are going to use this formula later on, so I'm going to rewrite this as 3i over n. And I did realize I have been using I, and notice that like for instance in these formulas, and this I is not the imaginary number that is equal to the square root of minus 1, okay? So be careful of that. I am just using it as a natural number. And we use I because of index, because it's the first letter of index. So just don't, hopefully don't get confused about that. Okay, so now we are ready to write down the integral of, here we have x cubed minus 6x dx. And remember, this is the limit as n goes to infinity of the sum of, I put my delta x first, so delta x times the sum from I equals 1 to n of f evaluated at that sample point. Now remember, for us, maybe do this in a different color. So for us, we're using right endpoints. Actually, maybe it's good to do it in the same color as that one. Right endpoints means we're going to use, so xi star is going to be equal to just xi. Okay, and so that's why this is kind of convenient to use right endpoints, because this is how this works out. So if you were to look at your interval, knowing that you start at x0, end at xn, and when you jump by 1, you see that x1 corresponds to the first interval, x2 corresponds to the second interval, and so on. Xi will correspond to the ith interval. Okay. Right, so we're going to go ahead and just replace that xi star with xi. Okay. Right, so we'll do that in the next step, and we will also at the same time replace delta x with our formula, which is just 3 over n. So I'm taking that from up here. And we get the sum from I equals 1 to n of f of 3, oops, not yet, xi. Okay, now, okay, so we can, like I was indicating there, we do know what xi is equal to because we computed it right here, right? We found this formula, so we're going to go ahead and plug that in for xi. Oops. Limit as n goes to infinity of f of 3i over n, right? Okay, now we've basically plugged in everything that we figured out, all of the things that we found formulas for. The only thing that we haven't used is the actual formula for our function, which was x cubed minus 6x, right? So we are going to go ahead and actually write out what this will be given that f is equal to x cubed minus 6x. Okay, so all we do is plug in 3i over n, and we get 6 times 3i over n, like that. And so this sum is of this whole thing, just to make that clear. Okay, and so just to do a little bit more simplification to make the next step a little bit easier, I'm going to go ahead and simplify these and actually distribute this cube to each term, so, or, you know, each part of that fraction. Wait, okay, make a little bit more room for myself. Here we have 27, so 3 cubed times I cubed over n cubed minus 18i over n. Okay, so that is going to be our answer, nicely simplified and ready to go to take the limit, right? Okay, so next, in part B, we want to use our summation formulas that I gave on the first page, so these ones up here, and we want to use them to actually compute this limit. So as you can see, it doesn't look like a very friendly limit to try to compute right now, but we will be able to once we use those formulas. So this may or may not fit in this space. I'm going to try to make it fit in this space. Unfortunately, I didn't do the formatting of this too perfectly. So this is going to give us, when we take this limit, the definite integral from 0 to 3 of this function. So since we have it right here, I won't copy it down again. I will just move to start simplifying. So remember one of the properties that we had, so I'm going to now use this property. So we have something minus something else. I can split that into two separate sums. So I'm going to go ahead and do that. So we have 3 over n on the outside. I'll make sure to use parentheses so that we remember to distribute that to each sum after we split these. So I equals 1 to n, 18i over n. Okay, now what we can do is use this property of the sum. So this one was where we could pull out a constant, and so we are going to go ahead and do that. So I will have 3n times, here the 27 is obviously a constant, but also the n cubed is a constant. So even though we're leaving n as a variable because we want to take the limit as n goes to infinity, when it comes to how this sum is seeing the inside of this sum, what is changing is I. So n cubed is not dependent on I, so it really is a constant as far as this sum is concerned. So the way that you figure out whether something is a constant or not is just to ask yourself, well, is the thing I'm trying to pull it out of, is that dependent on what is inside, right? And so if I try to pull the I cubed out, the variable for the sum is I, and so I cannot pull the I cubed out, but n cubed does not depend on I, so I can pull that out. Okay? And so it's nice to always use the same variables so that you don't have to rethink this every time. You just know that when it comes to these sums, if you used I as your index, you can pull the n's out, but you can't pull anything involving I out. Okay, and so we'll do the same thing here. We'll pull out the 18 over n of I. Okay, so now what we have is we have two sums that actually correspond to formulas that we were given up here that were listed. So we got the sum from I equals 1 to n of I, and we have a formula for it, right? And also I cubed was one that we have a formula for. So we're going to go ahead and replace those with the formulas. So we'll go ahead and do that now. So 3 over n, 27 over n cubed. The formula for I cubed, I am pretty sure it was, right, it should be n times n plus 1 over 2 squared, and 18 over n, and that one is n times n plus 1 over 2 without the square. And just in case you are wondering right now, you do not need to memorize these formulas, these ones up here. I will give you these, so don't worry about memorizing them. On an exam or a quiz, you'll have them. Okay, now we have something in terms of n. We just need to simplify it so that we can actually see what's going on and try to evaluate the limit, right? So now this is more of a normal limit that we might encounter, or we might have encountered before. So let me go ahead and distribute this 3n, since that's been hanging out front this whole time. And we would get 27 times 3 would be 81 over n to the 4th times, I'm going to go ahead and distribute this exponent 2 to each piece of this fraction right now, so I don't forget to do that. So that would be n squared. We would have n plus 1 squared, and in the bottom 4. Okay. So in fact, maybe I will add this to the formula up here. So maybe it would be good to note that this is equal to n squared times n plus 1 squared over 4. Okay. Now, what we have in the next piece, remember we have our 3 over n, and then we also have this this other stuff. So I'm going to go ahead and simplify this now, just to make things a little bit easier. So we can get some cancellation. We would get be left with 9 times n plus 1, right? And then let's go ahead and try to simplify some more. So in this first term, we have n to the 4th in the denominator, and we have n squared in the numerator, so we can do some cancellation there, and then we will have a little bit less to deal with. We'll have 81 times n plus 1 squared in the numerator and 4n squared in the denominator. And then simplifying this, we would have 27 n plus 1 over n, right? Okay, now where, I see, okay. 27 times n plus 1 over n. Now to evaluate this, we can go ahead and notice that instead of, well, there are a couple ways you could go about doing this. So you can choose whichever way you think is most intuitive, but one option is to combine these two fractions and then take the limit, and that will always give you an answer. But it is a bit more work because you have to find a common denominator, and you could make an algebra mistake. So another option is to compute these separately, and just so long as we don't get infinity minus infinity, then our limit laws will tell us that the limit of this whole thing, right, is equal to the limit of the first thing minus the limit of the second thing. And so since I already know the answer, I am kind of cheating, but we're going to go ahead and do it the second way because I know it will work out. Okay, so in this case, I'm going to go ahead and pull out that constant like we can do with limits, and then we're left with n squared, or maybe we'll multiply this part out. So this is n squared plus 2n plus 1 over 4n squared. And then we'll get, pull out the constant there too. Here, and I can even simplify this n plus 1 over n a little bit more. So if I split this into two fractions, I would get 1 plus 1 over n. Right, and then you can work this out, but this limit right here, since the degree of the numerator matches the degree of the denominator, you may have noticed when we have been working through examples that when that happens, we get that this is going to be the constant in front of the leading constant of the numerator over the leading constant of the denominator. If you don't remember that, you can just work it out by dividing the top and bottom by n squared like we normally do. but you will get an answer of 1/4 in that case. And then here it should be not too hard to see that this will go to 1. So this limit as n goes to infinity will be 1 plus 0 because 1 over n goes to 0. So we get 81 over 4 squared minus 27. And so we can go ahead and work this out to get a final answer. So 81 minus 27 times 16 over 16. This is not fun, but in any case, you will get a number. So this would be negative 351 over 16. Okay, so that is the end of this very long problem. I know it was very long and somewhat painful. Just remember that when we were first doing derivatives, we had to go through these very long calculations just to take the derivative of a pretty simple function. And then later we learned derivative rules that made it a lot easier. So that is going to be the same case here, but we won't learn these rules until Calc 2. So if you're planning on continuing on to Calc 2, this will get much easier to compute these. We'll learn some rules and things that you can do to compute them, but for now, we're working with the definition. Okay. So in the next video, we will talk about properties of the definite integral.